Okay. All right. Thank you again for inviting me. I'm sorry I couldn't make it out to be with you all in person. But today I'll be talking about a little different topic. So determine the origin of rogue planets. So is it born free or kicked out? This kind of started as like a small pet project, but it's actually kind of developed into something very interesting. So I just want to share my results. And so this is done in part with collaborators with William DeRocco at University of Maryland and Matthew DeFurio at UT Austin. And so, yeah, like I said, my name is Jeremy Smallwood. I'm currently a Dodge Family Prize postdoctoral fellow at University of Oklahoma. But I will start as assistant professor at Baylor University starting August 1st. So I have a quick kind of advertisement, so sorry about that. Baylor is actually the oldest continuously operated university in Texas. It's founded in 1845. It's one of the top 100 universities in the US, and it's an R1 research university. It has one of the largest science buildings in the US, as you can see on the right. It has a very nice football stadium right along the Brazos River. And the mascot for Baylor is actually the Bears. And we have two live bears on campus that are the mascots. So the reason why I'm advertising is that I do have funds for a postdoc that I'm hiring, or going the listing will be posted this coming fall for a start date of fall 2027. So I know it's a little early, but I just wanted to put it out there. If you or anyone is if you know is interested, please get in contact and look at that job posting in the fall. Okay. All right. So now let's get started. So I think we've all seen this type of figure before. So what I'm going to show is the current exoplanet population. This will kind of be a short video going through time of the observations of exoplanets. On the y-axis, this is the mass relative to Jupiter, and on the x, it's the distance relative to Earth. As time goes on, we discover more and more exoplanets, and we start to see kind of these three populations: very large planets close in, kind of larger planets further away, and kind of less massive planets closer to the stars. Like I said, we've seen this before, but there's one issue with this plot. Can someone point out what the issue is?
The plotting particles should be rendering them.
Sorry, no, not that. Um, the x-axis stops at 10 to the 4. Okay, really, this plot should go out to infinity. Okay, so we know that there's these free floating, these rogue planets out there. We don't know what their kind of mass distribution is, and so what is what is the big questions that we want to answer in kind of this emerging field of these free floating planets is what this mass distribution is, and how does that kind of compare to these bound planets that we see. Okay. I just want to point out that the Nancy Grace Rowan Space Telescope is scheduled to launch this September. This will detect more and more free floating planets through microlensing. These are just kind of simulated data points, but Romans anticipated to observe up to 1,000 more free floating planets than we've already detected. On top of that, it can detect more bound planets, even down to moon sizes. Very looking forward to kind of seeing what Roman can detect. And I was this time last year, I was visiting Goddard, and then I snapped a photo of Roman being assembled. And so I think it's all set to go. And it's actually, I think, one of the first telescopes that's actually going to launch earlier than anticipated. It was supposed to launch in October, and it's got pushed to September. So hopefully it goes a very good launch. So I mentioned free-floating planets, but what are free-floating planets? So these are bodies of planetary mass that are not gravitationally bound to any star. So they're just drifting in deep space. They're also called rogue planets, or you'll see maybe the term called free-floating planetary mass objects. And so the kind of the mass range for these free-floating planets is what the name suggests, is that they're planetary masses, so they can be about 13 Jupiter mass or below. Anything above 13 Jupiter mass to about 75 would be in the brown dwarf regime, and beyond 75, that would be considered a star where you have hydrogen burning. So where do we find these free-floating planets? Usually they're found in star-forming regions. For example, you can have some in Orionis or Upper Sco. I'll show you an image, I think, on the next slide. And why do they matter? Well, in part, they kind of probe the low mass end of star formation, and they're kind of linked to the efficiency of planetary ejections, which I'll talk about. And the most important thing that this is kind of quite recent is that they can host disks of their own. And so that's what I'll be talking a lot and showing some nice simulations later. And so, how do we find these planets without stars? Well, there's two ways. The first is direct imaging. Really young free-flowing planets are quite self-luminous. They glow in the infrared for tens of millions of years after their formation or after they're ejected. And so there's a lot of deep surveys of young clusters that can actually detect and image these free-floating planets. So the image on the right is of Upper Sco, which they've detected roughly 115 rogue planet candidates. And these are very nice if you can directly image them because you're allowed for follow-up observations, such as like atmospheric observations. If you want to do some follow-up of their disks, if they do have some, or look at accretion. Um, but the limitation for the direct imaging is that it only works for very young and nearby massive objects. The second way to find free-flowing planets is gravitational lensing. I think most are familiar with gravitational lensing, but the FFP, the free-flowing planet will pass in front of a background star and briefly magnify it. And so you have this magnification can happen, can last for hours to days. So this way to observe is more sensitive to old cold free-floating planets down to even terrestrial masses. And there's a lot of telescopes currently that are kind of looking for free-floating planets. One is the optical gravitational lensing experiment that's in University of Warsaw. And we have the microlensing in astrophysics telescope that's in New Zealand. And the KMT is the Korea microlensing telescope. So we have a lot of these observatories that are kind of continuously looking and detecting free-floating planets. Um, the only issue is that you really don't know the mass of or distance of these free floating planets because there's a degeneracy, and so you need parallax to kind of break that degeneracy either with Spitzer or Gaia, and I will show you that there's actually one case that one free floating planet that we've broken the degeneracy using Gaia, and so it's a very interesting system, and I'll briefly mention that later. So the limitations for the microlensing is that it's one-off events, so there's really no follow-up characterization. So how many free-flowing planets are out there in the galaxy? So there's a lot of surveys that have been done. Assuming all 2021 analyzed the MOA-2 survey data towards the galactic bulge. They looked at 3,500 microlensing events. And what they found is that there is a clear excess of short duration events with Einstein times of less than 5 days. And this excess is not predicted by if you just take into account the current galactic population of stars, brown dwarfs, and bound planets. Though that population cannot uh, uh, cannot form or cannot explain this excess of these short duration events. And so what they've done, hopefully you don't ask me any questions about this plot on the right, but what they've done is they've added a new power law, which is the green one, which are considered unbound planets or very wide orbit planets. And so if you integrate this kind of curve down to one Earth mass, you get about 20 free-floating planets per star. There's other groups that have done similar calculations, and they kind of range maybe from 5 to 10 to 20 free-flowing planets per star. So if this is actually true, that means the free-flowing planet population is actually the majority of planetary bodies in the galaxy and not bound planets, which I think is quite interesting. So how do you actually form free-floating planets? There's two general ways. I like to call it star-like and planet-like. So for the star-like, you form like in situ formation, similar to just a low-mass star, where you have a turbulent fragmentation of a molecular cloud, and you can just create a very low mass planet. Or you can have photoerosion of prestellar cores by nearby OB stars. I've used about 75% of my artistic ability to make these figures here on the bottom, but this just shows this star-like collapse to make a free-floating planet. The other more interesting one is it forms like planet-like. So you form a normal planet that's embedded in a protoplanetary disk, but then something happens where it's ejected, dynamically ejected. And so there's different types of ejection channels. Some include planet-planet scattering, stellar flybys, cluster encounters, or instabilities around binary or triple star systems. And this figure I made on the bottom just kind of represents a planet-planet scattering channel where you can kick out a planet. But these channels do differ from one another. So this is from Gavin Coleman and Will Dorocco just last year. Kind of wanted to probe what the galactic population of these free-floating planets would actually look like based on different ejection channels. And so what you find on the what you see on the x-axis is the planet mass, and then on the y-axis is the number of ejected planets, or just the number of free-floating planets. And so really where you reach and there's different there's a lot going on in this figure. And basically what we have is kind of different channels that separate these curves. And so for planet-planet scattering, it really dominates the low mass end of free-floating planets. That's what they're predicting. The more higher mass free-floating planets or they find are due by binary ejections. Um, they don't kind of look at stellar flybys or several other different channels. Their main channels they look at are binaries and then planet-planet scattering. But they're just the takeaway is that planet-planet scattering can produce a lot of low mass, more low mass free-floating planets, and then the binary ejections will create more higher mass free-floating planets. But what we find is that if you look more closely at kind of these larger mass free-floating planets, they show signs of disks. And so this was a study by Rodriguez et al. Just last year, where they looked at the disk fraction using the unwise excess survey on upper SCO. And they looked about 17 to 40 free-floating planets. And what they find is that as you decrease your mass, you actually increase the number of excess fraction, which means you increase the number of the disk probability. So the more lower mass planets show an excess of having more disks around them. And also just last year, this is by Damien et al. They did some follow-up observations of 8 known free-floating planets and looked at their spectrum. And what they found is that 6 of the 8 showed signs of disks. And so there's six of these disks showed the 10 micron silicate features, which is evidence of dust processing and crystallization, which means that these free-floating planets with disks they could be going under active moon formation, even though they're not orbiting any star. And also, some of the disks they found methane and ethane emission, and the strongest of these was in CHA 1107 7626, which this disk around this free-floating planet resembles the very hydrocarbon-rich disk around the low mass star ISO-CHAL 147. And so there's a lot of similarities in disks around free-floating planets to very low mass stars. And so kind of going in more detail about this free-floating planet, it actually was seen just last year to be actively accreting free-floating planet. And so this free-floating planet has a mass of 5 to 10 Jupiter mass. And it's, again, like I just mentioned, it has a lot of hydrocarbon emission lines, and it has multiple accretion line driven emission lines, which are seen to be presumed to be from an actively accreting disk. And so what they show here in their plot is the Paishon gamma line, which is a good indicator of episodic accretion or accretion bursts. And what happens when you actually have an accretion burst is that this line increases its flux and also broadens. And so this accretion event was seen taking place in April all the way to August. And so it's still getting it's still the accretion is getting larger, yeah, even in August. Um, and so this is the first time that such a low mass object was seen to undergo an episodic accretion event. And again, this has to be coming from a disk. And this planet here this is one I mentioned before that's very interesting. We don't know if it has a disk or not because it was found through microlensing. But this is the first time that we can actually constrain the mass and distance of this free floating planet because there were actually two simultaneous observations from Earth, from the KMT, and from Gaia. So this is actually a coincidence that Gaia picked this event up at the same time, or else we wouldn't be able to break the degeneracy. And so this free floating planet is actually a Saturn mass object of 0.22 Jupiter mass. And the velocity that it's moving relative to the nearby stars is very, very fast. It's 90 kilometers per second. And so just to put that in context, none of the theoretical models for ejection can get to this velocity. So even planet-planet scattering models, maybe 1 to 10 kilometers per second, this is almost an order of magnitude more than that. So this is a very, very weird object, and right now we don't have any models to explain the very high velocity that it's moving at. Okay. So really the open questions, it's like what channel dominates the free floating planet population? How long do these disks survive? Can these disks produce moons? And again, we have a lot of upcoming observations from Roman and even ALMA that might be able to help with the population of free floating planets and their disks. The main thing I wanted to look at is, can these ejected FFPs have disks? Or sorry, how can they have these disks? Okay. So what I'll do this really quickly because I spent too much time on my introduction. But we know that planets embedded in disks can form circumplanetary disks. We have two examples, PBS-70 and WISPIT-2b. We know that there's stellar flybys that can interact with disks. And so if you kind of put these together, you can kind of get this schematic. Here I used 100% of my artistic ability to make this figure. Where if you have a planet-like formation of a free-floating planet, you have an embedded planet with a circumplanetary disk, you can have some sort of external perturbation. In this case, I use a flyby that maybe could perturb the planet, eject the planet, and see if the CPD can retain, or the planet can retain its CPD during the ejection. You might have a much more truncated disk. Unlike if you form a planet in situ, you might have a much more extended disk. And so kind of the hypothesis that we're going with is that you can maybe use the disk size as a diagnostic for the formation channel of these free-floating planets that have disks. So I run a lot of in-body simulations to see what parameters the flyby can actually perturb the planet and cause it to be ejected and thus a free-floating planet. As you can see in the movie here, this purple dot is the planet that's been ejected from the encounter. So I run a total of 50,000 simulations. So here's a plot of 40,000 of them. Where I alter the inclination of the flyby and I vary the periastron distance of the flyby. The gray color it means the planet remains bound in the simulation. The red is the planet's captured by the stellar flyby, and the blue is free floating. And these four different panels just show a different initial true anomaly of the planet, which does affect the outcome a little bit. And so what you see here is that if I plot here, so this is the probability of each encounter as a function of their inclination. For coplanar encounters, the highest probability is actually to be ejected as a free-floating planet. As you kind of increase your inclination of your flyby, that probability decreases, and the most higher probability is to remain bound. But for coplanar parabolic encounters, the highest probability is to be unbound. And it also varies, like I said, it also varies with the true anomaly. So this is for an inclined, sorry, this is a coplanar encounter. And this is looking at if you change your true anomaly of your planet as a function of your periastron distance, you get the striations just because it depends on where the planet is in relation to when the periastron of the flyby hits. And so this star here is the parameters I pick for my phantom simulation. Um, and so I know this is the Phantom workshop, so I finally got to my Phantom simulation. So what I've done here is that I have a 2.5 mass Jupiter planet embedded in a protoplanetary disk. I use APR that's centered around the planet to get higher resolution so I can actually resolve the CPD. I also start with a pre-carved gap. The reason why is that this kind of speeds up the evolution and the computational, so I don't have to actually sit there and wait for a plant to carve the gap. I can start with the gap, and I can save some computational time, and then just focus on the evolution of the CPD. So here's the evolution of the CPD without any stellar flyby. This is just the planet embedded in the disk, and this is in the co-rotation frame. Uh, then I Oh, sorry. And then I add the stellar flyby. And again, this is in the co-rotating frame, so it's going to look a little weird. But as the flyby comes in, it will then eject the planet. If you look at the middle panel here, the planet is ejected and it does retain its disk. Um, and so we can kind of look at how the disk evolves in time. So on the left panel here, I'm showing the surface density profile as a function of radius. This is of the CPD. The black one is the initial profile, and the blue is the profile shortly after the ejection. It seems a little more truncated, but really this tail here is the streams or the tidal stream of spirals that are connecting the CPD to the actual PPD. And what I show here is the shaded regions are the different levels of refinement for the APR. On the bottom panel, I show the azimuthal velocity. Sorry, I should have labeled these, but this dotted line here is the Keplerian rotation, and the dashed one is the pressure induced Keplerian. So it's like a sub-Keplerian profile. And so when the disk is when the CPD is embedded in the PPD, the CPD is subcapillarian, and so you can actually measure the size of the disk through this. So the time it deviates from the Keplerian or subcapillarian curves, that's the size of the disk. And so initially the size of the CPD is about zero point 0.3 Hill radii of the planet, which has been confirmed in other simulations and also grid-based simulations. About the size is about 0.3 Hill radii. But as the planet's ejected with its disk, it goes perfectly Keplerian, and it actually becomes a little larger. So the disk is actually more truncated when it's embedded in the disk, which makes sense. Once it's ejected, it gets a little larger. And so if you look at the eccentricity profile of the disk, this is also interesting in the context of moon formation. So before the ejection, the disk is relatively eccentric. But after it's ejected, the eccentricity decreases, and so the disk is actually more stable, which might be easier to form moons and for dust to grow. And this bottom panel here shows just the mass of the CPD to the initial mass of the protoplanetary disk. And as it makes sense, it just decrease over time because we're accreting onto the planet, and there's nothing to be able to feed or supply mass to that CPD after it's ejected. So I'm running out of time. So this is kind of my last slide here. So really want to connect to observations. And so this part has been quite challenging. So I'm happy if everyone has any other ideas. But the main premise is that we thought we could maybe use the disk size to distinguish the formation mechanism. And so if you think about objects that are forming in situ, they might have a disk size, and there's actually a scaling relation from Sean Andrews in 2018. But I'm not sure if this scaling relation can extrapolate all the way down to what the masses we're looking at is like a few Jupiter mass or tens of Jupiter masses. And so if you kind of go back at this cartoon, is that we think that in an ejected planet, that the CPD of an injected planet should be more truncated than say its same mass counterpart formed in situ, should have a much more extended disk. The only issue is that we don't have any observations of disks or the sizes of disks down to these masses. And so I'm a part of two ALMA proposals. that have just been were just submitted back in April to actually measure disk sizes of these free floating planets that actually have disks. So hopefully we can get some good. Hopefully those are accepted, and we can get some good constraints on the disk sizes. But one thing we can maybe say is that if you're forming if your CPD if your free floating planet is ejected, the size of the CPD should vary because we actually don't know where that planet's being ejected is within the disk. It could be ejected at 100 AU, it could be ejected at 50 AU. We don't know where the planet is. The planet location actually affects how the disk size is how large the disk is. So like I mentioned before, the disk can be out to zero point 0.3 hill radii, but the hill radii depends on the semi directions of the planet. And so if you measure disk sizes that may have been ejected, you should see a large spread in actually the disk size for a given mass planet. Unlike if it's formed in situ, at a given mass, it should have a much narrow range of the disk size. So perhaps we could use that to distinguish these formation mechanisms based on their disks, but we're still looking into that. So I'm happy if anyone has any other ideas. I know I'm right out of time, so I'll leave my summary up and I'm happy to take any questions. Thank you.
Hi, Jeremy. Thank you very much for the presentation. Happy to see such new topics coming up. I have a question regarding like the accretion rates if you of two subjects. Do you have any idea of numbers on this? Because that would basically determine the disk lifetime, which would be interesting to constrain as well.
Yeah, I haven't looked at the accretion rates from my simulations, if that's what you mean. I mean the observations they've detected accretion. I don't know the exact numbers of those accretion rates, but that's something I could look at in my simulations is what the accretion rate is. But I haven't done that yet.
I mean, the idea behind my question is basically since I'm a bit surprised by the fact that you have so many disks around those objects, and since we have talked a lot during the workshop about infall, infall could happen also for those low mass objects. And
Mhm.
in that case, to me, the accretion rate should be very high, whereas if the disk, the planet has been ejected and retained its disk, probably the accretion rate is a bit lower. I don't know, just throwing out how it is, but could be worth looking at that.
Yeah, okay, yeah, sounds good. Yeah, we can surely I can follow up with you on that.
Questions? Jeremy, I have a question. So for the high velocity free floating planet, so when you have a circumbinary planet at the main sequence stage, and then the two stars may go through some messy interactions, will that orbit be destabilized enough for the planet to come close enough to the potentials to be slingshotted out?
Yes. Sorry, what was the question?
The question is that would that explain a high velocity?
Oh, I see. Okay, yeah. So they've done those simulations. I believe that channel maybe can get up to 30 or 40 kilometers per second. But none of the models that I know of can get up to like around 90.
Okay. Any more questions? Yep.
Question about the ejection. So I don't know if you said this, where is the CPD typically at that the flyby will then cause the ejection? Like how close to the star is it?
In this case for the flyby.
Yeah.
Um, I mean it really
Like did you
depends.
test various scenarios also?
Yeah. So I've just tested 100 to 200. So this is a very close encounter. As you can see, like these kind of islands of being ejected or captured, they start to decrease as you increase your periastron, which makes sense. So at some point, if your periastron is far enough, you won't get any ejections. But yeah, there is kind of a sweet spot to get these ejections.
Sorry, I think I was asking how close is the planet to the center star?
Oh, okay. Sorry. Yeah. So I just did 100 AU, which is quite far.
Yeah.
I mean, again, yeah, if you do a closer planet, you would need a closer flyby to kind of to make it ejected.
Yeah. Okay.
Ali?
Yeah, I just had a simple question. In one of your figures, you mentioned measuring disk eccentricity. I just wanted to ask what do you mean by that? Is it the shape of the disk or something about the energetics of it?
Yeah, so this is a density weighted eccentricity of the disk. And so I measure through the eccentricity vector. Um, is that your question in this figure here?
Oh, yeah, well, kind of. I don't know what eccentricity vectors are, so yeah.
Yeah,
But
so this is just a density weighted average. So I'm averaging the whole disk, and that's what I'm showing here. So it's not any particular radius. It's just it's averaged over the whole disk.
and is there any like physical and like what does it tell you
I
doing
mean
this?
so yeah, the more eccentric it is, the kind of more oval shaped the orbits are. But in this case, what I really care about if it's more eccentric, that means there's actually if you look at gas and dust, there's a higher relative velocity in the more eccentric disk, which makes dust growth even harder to proceed. And so if you need for a lower eccentric disk, there should be less collisions, and so in this case, like moon formation should happen more easier in a free floating planet versus a planet that's embedded in the protoplanetary disk.
Okay. We can thank Jeremy again.